Okay, this is lesson 4.4, exponential expressions and equations. Up to this point, we've just been working with expressions. Today, we're actually going to visit equations. Let's square away a little terminology first. Words that you've seen so far in this unit have been simplify and evaluate. Simplify means to express answers with positive exponents. So taking something that looks complicated and rewriting it as a single power with a positive exponent. If there's numbers involved, coefficients or constant, we need to reduce them. And if there are multiple variables that are the same, we need to express it as a single power. If there are more than one variable, like x and y, for example, then there'll be a single power for each of those variables. Evaluate, you'd be given when, or the question would say evaluate, when they want a single numerical answer. So something that doesn't involve variables, and we can actually turn this into a single number by simplifying. Today we're going to look at solve, and specifically we're going to look at solving when the variable is in the exponent. So this is called an exponential equation because the exponent is the variable. And today we're going to look at 4 different strategies to solve for that variable. I can put the variable not in the exponent and have exponents and ask you to solve as well. Those ones are a little bit more straightforward. Like for example, if we had x squared, we could square root. Or if we had the square root of x, we could square both sides to start isolating. So working with exponents is pretty important still, and we'll do a couple examples of that in class, not in the lesson. The focus of this lesson is how to solve when the variable is the exponent. So let's look at 4 strategies. The first one is called guess and check. How you guess and check. If we are asked to solve this equation, your first guess is kind of just a shot in the dark. You really don't know what's going to happen, and you kind of work off your answer to come up with a more accurate guess. So let's try a value of 1 for x and see what happens to the left side and the right side. We'll know that we guessed the right value of x when left side and right side are equal. The left side of the equation says 8 to the exponent x minus 2. So if I plug in my 1 for x, I'd get 8 to the exponent 1 minus 2, which is 8 to the exponent negative 1, which using negative exponent rules is 1 over 8. If I put 1 on the right side, I get 2 to the exponent 1 plus 4, which is 2 to the exponent 5, which is 32. So 32 and 8 are not the same thing. So 1 is not the answer. So now we got to take another shot. The question is, should we guess a number higher or lower? You don't really know. You might be able to reason it out. I'm going to guess 0 and see what happens. 0. If my answers get further apart, maybe I'll try going in a different direction. If they get closer, I'll keep going in that direction. If I put in 0, I get 8 to the exponent 0 minus 2, which is 8 to the exponent minus 2, which would be 1 over 64. Okay, that's getting further away. Let's see what's happening on the right side. 2, 0 plus 4. That would be 4, and that's 16. Not really sure if that's closer or further apart. Kind of looks further apart. I'm going to try the other direction. Let's make a significant shift. If I try to reason this out, I'm going to need this exponent to be pretty big if I want it to match this one, because if as the x gets bigger, the exponent on both is going to get bigger. But the base 8 is bigger than the base 2, so it shouldn't be huge. I'm going to try 8. See what happens here. 8 to the exponent 8 minus 2. This might be too big. 8 to the exponent 6 is 2, 6, 2, 1, 4, 4. Wow. All right, let's try 8 on the other side. I don't think it's 8. 8 plus 4, which is 2 to the 12. That's pretty big too, but I don't think it's as big as the other one. That would be 4096. All right, they're both big. This one's now bigger. My guess is it's somewhere between 0 and 8. Let's go with 5. 8 to the exponent 5 minus 2 is 8 to the exponent 3, which is 64 times 8 is 512. This could be it. Let's try 2 to the exponent 5 plus 4 is 2 to the exponent 9. Yeah, 512. So it wasn't 8, but it definitely was 5. Yes. So we were able to guess it. It took 4 guesses. I think I got pretty lucky on this one. So I don't know that this is the best strategy to use. In this course, sometimes this is the only strategy we have. Next year in advanced functions, you'll learn a strategy that will definitely work every time. But there is a strategy that we could have solved this one quicker, and it's the next strategy. And this is the strategy we're going to use most often in this course, and it's rewriting the powers with a common base. So 2 and 8 have something in common. They're both powers of 2. 8 is 2 to the power of 3, and 2 is 2 to the power of 1. You can change those numbers to be written as a common base of 2, just like 4 and 2. If I was given this equation, I could do guess and check just like I did on the last example. But since the bases 4 and 2 have a base in common, which is 2, we can change the bases. And I'll show you what I mean. If you were to write down the powers of 2, 2 to the exponent 0 is 1, 2 to the exponent 1 is 2, 2 to the exponent 2 is 4, 2 to the exponent 3 is 8, and you can even go in the other direction. 2 to the exponent negative 1 is a half, 2 to the exponent negative 2 is 1/4, and 2 to the exponent negative 3 is 1/8. If you ever have an exponential that has any of these numbers as the base, you can change them to a base of 2 if you add in an exponent. And we're going to take advantage of this when we do solving exponential equations, because in the case of this example, 4 and 2 can be written as 2 to the exponent something. And I'll show you why that's important. I'm going to change 4 to 2 to the exponent 2. And 2 already is a base of 2. Now, why would we do this? Well, we would do this because if we can make the bases the same, the only thing that would be different is the exponents. If the bases are the same, we can say the exponents then have to be the same because this is an equation, and we can just set the exponents equal to each other and solve. We need to do one more step here. We've got 2 to the exponent 2 to the exponent x plus 1. What happens when you have an exponent of an exponent? Well, you multiply them. So this is 2 to the exponent 2 times x plus 1. And this is 2 to the exponent x minus 1. Since the bases are the same, for this to be equal, the exponents would have to be equal. So the next step, once you've made the bases the same, is just to ignore the bases and say the bases are already the same. That means the exponents have to be the same. And now you can just solve for x. And you're not working with an exponential equation anymore. Now you're just working with a linear equation. So distribute, we get 2x plus 2, x minus 1. If I collect my x's on one side, I end up with 2x minus x. And if I move the 2 to the other side, I get minus 2. 2x minus x is x. Negative 1 and negative 2 is negative 3. The answer is negative 3. And you could go back and check, put negative 3 into each of the exponents for x, and you would end up with something that is equal. So this is called changing the base, or rewriting powers with a common base. And it's neat because once you have the bases the same, the only thing that you can set equal now, or need to consider, is that the exponents also have to be the same. For the left side to equal the right side, the exponents would have to be equal because the bases are already equal. So that's a nice strategy you can use when you can change both bases to match. If you can't change both bases to match, you cannot use this strategy. You would have to do guess and check, or wait till next year when you learn about logarithms. A third strategy is called the common factor strategy. And you can use this strategy when you have two terms with x and they have something in common. So for example, we have two terms with x Both have a base of 3, which would be neat, and we could set them equal to each other, but the problem is this 216. There's an extra term. If we didn't have that term, and those were set equal, we could just solve by setting the exponents equal, and it'd be a pretty easy question. But because we have this extra number, we can't quite do that. We need there to only be one term with x if you have 3 terms. And the way we can do that is we can do some common factoring. 3 to the exponent x plus 2, if you remember your exponent rules, when you would add exponents is when you were multiplying. So this term came from 3 to the exponent x times 3 to the exponent 2. Because if you were multiplying these, you would add the exponents. It's like using the exponent rules in reverse. Using the exponent rules in reverse allows you to see something. And what I want you to see is that 3 to the exponent x is now common to these 2 terms. So we can common factor it from those 2 terms. And that would leave us with 3 to the exponent 2 minus, if you take 3 to the exponent x and common factor it away, you're just left with 1. 3 squared is 9, and 9 minus 1 is 8. So now we have 3 to the exponent x times 8. And now we can divide the 8 away. And we end up with 3 to the exponent x equals 216 divided by 8 is 27. And now how do you solve this? Well, you could guess and check, or you could change 27 to have the same base as 3 to the exponent x. So the question is there 3 to the exponent something that equals 27? And the answer is, yes there is. 3 to the exponent 3 is 27. And now the bases are the same, so you can set the exponents equal. What happens if you set these exponents equal is you get the answer. X equals 3. And you could go back and check, and you could see, in fact, that if you plug in 3, you get 216. So this strategy is used when you have 2 terms that have the same base, x in the exponent, and there's a third term. The strategy before was used when you just had 2 terms on either side of the equal sign, both with an x in the numerator, in the exponent. Okay, so common factor when there's 3 terms and there's a term that's common. The last one is called variable substitution, and this one is the most advanced of the strategies. Variable substitution you use when you have multiple terms, so in this case we have 3, and we create something that looks pretty complicated. We want to simplify it by doing a variable substitution. This is a variable substitution, but it's also a quadratic exponential equation. And I'll show you what I mean by a quadratic exponential equation, because that sounds intimidating. We have 2 terms with x in the exponent, but they don't have a common base. So our first step is going to be, we're going to change these so they have a common base. Fortunately, 5 to the exponent 2 is 25. So that's an easy change to get a base of 5. All of the questions you're going to do, there will be some sort of common base. And if there's not, you will use guess and check. So in this case, there is a common base. So over here on this side, I'm going to show you how to change it. 25 to the exponent x. That's the same as 5 to the exponent 2 to the exponent x, because 5 to the exponent 2 is 25. Now, 2 times x is the same as x times 2. Order doesn't matter. So I'm going to change the order and write this as 5 to the exponent x squared. Because if I multiply these, I still get 2x. The reason I'm changing the order is so that you can see 5 to the exponent x squared minus 30, 5 to the exponent of x plus 125 equals 0. The reason I'm changing is so that you can see that this is quadratic. You may be able to see it right now, and it's okay if you can't, but there's a term squared minus a term that has a coefficient times a variable term plus a constant term. And that follows the format of a quadratic. And to really demonstrate it, you can use variable substitution. All that means is instead of 5 to the exponent x, that's the complicated part here, I'm just going to write the letter a. So over here I'm going to say let a equal 5 to the exponent x. And now you'll be able to see that it's quadratic. Ready? Instead of 5 to the exponent x, a squared minus 30. Instead of 5 to the exponent x, a, I'm not going to write that in brackets so it looks a little bit more obvious, plus 125. So now we have a squared minus 30a plus 125. That's clearly a quadratic. Okay, we've done some substitution, and now we have an equation that is quadratic after doing a variable substitution. Now we can just factor the quadratic. Look for numbers that multiply to 125 and add to negative 30. Since it's a simple trinomial, we can go right to factored form if you can think of those numbers. And those numbers are negative 25 and negative 5. And now you would solve this just like you solve a quadratic. You would take each of the factors, set them equal to 0, and solve. Here's the first one. Add 25 to both sides. A is 25. That's not the answer because a is 5 to the exponent x. So 5 to the exponent x is 25. And the question is, 5 to the exponent what is 25? Well, 5 to the exponent 2 is 25. So x is 2. But also, if we add 5 to both sides, a is 5. But 5x is what a is, so substitute it back. 5x equals 5. 5 to the exponent what is 5? 5 to the exponent 1 is 5. So x is 1. All right. Now, solving a quadratic exponential equation is kind of the outer limits of solving quadratic equations, or solving exponential equations. And this is something that you're going to revisit in grade 12. It's important for you to have an understanding of it right now, and just how much of an understanding, something we're going to continue to talk about in class tomorrow. But I needed to introduce it to you in the video, and we're going to do some examples of it in the video. This is quite a challenging concept that you're going to work on for 2 years, this year and again next year. Common factoring, again, another challenging concept that we're going to revisit in grade 11 or grade 12. But the guess and check method and rewriting powers with a common base, those are methods that we need to get to a point where we've mastered this year. Common factoring, variable substitution, we revisit next year. But mastering the first 2 concepts is pretty important. Okay, there's some extra practice. That's actually the practice homework for in class tomorrow. So that's it for lesson 4.4. Thanks for watching, and I'll see you next time.